The electric motor is a fundamental part of everyday life and is one of the key components to hobby electronics, as most kits come with at least one small motor, often a DC motor. In this video, we'll explain the basic motor types you'll encounter in hobby electronics. We all have a pretty firm idea of what a motor is, but the most broadest definition is any machine that converts energy into mechanical motion. In this case, we'll be talking about electric motors, so it converts electrical energy into mechanical motion. There are rotary motors and linear motors. In some cases, we'll be talking about motors versus things that might be motor-like, like actuators. Now, in terms of a rotary motor, it starts with electricity flowing into a coil. That coil creates a magnetic field. There's interaction between magnetic fields, and that causes force, and the force causes the shaft to rotate. In a linear motor, electricity flows into a straight line coil. This creates a field. Magnetized cartridge, also known as a forcer, is pulled along a track. Current switching causes smooth movement back and forth. There's a number of characteristics to motors: the torque, speed, power, efficiency, control precision, the response time, that's also known as dynamics, construction, the load characteristics, and thermal limits. Now, what are some of these motor characteristics? Well, let's start with the torque. That's how strongly a force can turn a shaft. Speed, that's how fast the motor or shaft is turning. And then there's power. This is the rate that the motor does work, and it's really just torque times speed. And then there's the efficiency, how much of the electrical energy is actually being put to use. 100% is impossible, about 80% is good. Anything below 50% is poor. And then control precision, how accurately and consistently you can control the motor's position, speed, or force. This is very important. Then we have our response time, also known as dynamics. This is how quickly the motor responds to change. The construction, this is how the motor is actually built or implemented. The load characteristics, how the motor behaves depending on what it's driving and how resistance changes over time. And then we have thermal limits, how much heat the motor can take before performance degrades or damage occurs to the motor. Now, this video is just going to focus on some small scale motors used in hobby electronics. Obviously, a single presentation isn't going to cover the sheer scale of motors, and I know very little, next to nothing about automotive electronics, but a couple of years ago I knew next to nothing about hobby electronics. So basically, what do we use them for in hobby electronics? Well, DC motors can be used for driving wheels on an RC car or robotic cars, small fans, conveyor belt models. Servo motors can be used for robotic arms and grippers, RC airplane control surfaces, and even pan and tilt camera systems. Stepper motors can be used for 3D printers, CNC machines. This is where it takes a piece, it moves it around, and essentially cuts it. Um, Automated camera sliders, so it'll slide the camera, left, right, up, down, whatever. And plotter machines. And then you've got brushless DC motors. Those can be used for all sorts of propellers, as well as do-it-yourself fans, turbines, etc. Now, we're really going to be talking about five categories of motor, and three of them are pretty similar. Um, you've got your DC motors. These are simple spinning motors. You'll often see them including in a hobby kit. They really just have a power and a ground wire. There's a little brush on the inside that touches surfaces to switch direction with current changes. Um, and yeah, that's pretty much it. You power them in one direction, they'll spin in a direction. You switch the wires, they switch to another. They're incredibly cheap, so you can replace them as needed. Then we have gear motors. That's just a DC motor with a gearbox. Trades speed for torque, so it can move stuff, lift loads, etc. Servo motors, you've got precision control and position. It actually uses a couple of different components to achieve this. Um, you'll often see a little micro servo included in the hobby kits. Stepper motors, very fixed position. It doesn't actually need to correct position because each step is so precise. And you've got both bipolar and unipolar for those. We're going to get into that. And then you have brushless DC motors. It eliminates the brushes, but it requires a thing known as electronic speed control, more efficiency, less heat, and longer lifespan as a result. All right, well, let's start talking about DC motors. Very simple, two wires. Motor spins, reverse the wires, it reverses directions. Very simple. The problem is that this a motor uses a lot of current compared to some of the other components we've talked to. A spinning motor alone can use 50 to 300 milliamps, and if it stalls, that could use half an amp to even 2 amps. It's crazy. This is well beyond what a microcontroller could safely handle, in some cases, even a breadboard. Now, we'll often use drivers to provide safe channels, both the logic control and the supply. And here's three examples. Notice what it can handle: channel peak. Mind you, in some cases with a channel peak, you'll want a pretty good heat sink on it. Most of the time, if you just search DC motor driver board, you're going to see L298Ns, and they'll have a good heat sink on them already. They'll pretty much have whatever you need. Um, they can handle pretty significant voltages and currents, whatnot. Has pulse width modulation and everything. When it has two channel, it can mean it can handle two DC motors, I believe, and yeah, I think so. Um, and also different speeds because of the pulse width modulation. And or it could actually be used for a stepper motor as well. And I think the other two can as well. They just have different characteristics. But they might not be handled like the NB6612FNG. That's a mouthful. It's supposed to be basically an upgrade to the previous one that I just mentioned. Um, it can take better peaks and continuous amperes. It has a wider breadth for the logic, but it can't take as much in terms of motor voltage. But anything that takes in excess of 12 volts should be pretty good for hobby. It just can't handle like 24-volt motors. Um, all right, here's just a basic illustration of a DC motor in every circuit. It's being driven by 6-volt power sources. This DC motor, rated for 6 volts, it in theory will go up to 600 revolutions per minute. Its starting currents is 2 amps, load level, etc. I've got it set with two-way switches so that we can reverse direction and everything. One, oop, so it's currently standing still here. So let's turn it on in one direction. So it started at about 2 amps and it's steadily coming down till it reaches a certain point. It's just gone up to 150. Let's see if boosting up the, okay, yeah, so boosting up the voltage 6 is the kind of the minimum, I guess. Oh no, it'll go up even faster. Okay. But yeah, it really kicks up in the amp. So I guess it's supposed to just operate on 6. All right, well, let's put it at 6 anyways. Reverse that. All right, okay. So it's sitting at 150 revolutions per minute at 6 volts at 1.5 amps. Yeah, this is a lot of amps. Now I can kick that back down. So it's at 0 amps. It's doing nothing. All right, let's reverse the direction. Same idea. So pretty simple concept here, but again, a lot of amps. Now, here's a question. What if we put a resistor in there? Well, we just put a 1K resistor. It doesn't move. It needs a certain amount of current to start moving. All right. Well, let's start reducing that down. I mean, we've already reduced it to 100 ohms, and it still ain't moving. We moved it even to 10, and it still ain't moving. So yeah, That ain't doing much of anything at this point. Oh no, we're starting to have an effect now. It's got to get to a certain point. It says starting current about 2 point, but actually it seems to be closer to maybe about 1.5. Oops. So we're getting a little motion here. Let's use it further. There we go. All right, here's an example in Falstad. We've got a DC motor in the middle. It is running, actually it's running down. Let me reset it. All right, so both things are set to ground. We're turning it on in one direction. You see the amps are climbing quickly. So it's well above 1 amp at this point. It keeps climbing. RPMs are going up. Now, this is kind of a slow, well, let's speed it up a little bit. Okay, it hit 3.5 and it's kind of easing off there. It's hovering around 99 RPMs, but yeah, 3.4 amps at 5 volts, doing 17.2 watts of power. Well, let's switch that off and see what happens. Okay, it goes all the way down. All right, let's switch to the opposite direction. Yeah, see, it's going all the way up to 3.5 amps. All right, let's look into operating a DC motor in SIMUIDE with an Uno. Let me just stop it and take a look. Now we have a L293 dual channel operating board here. Ignore the fact that there's not power or ground connected to it. Let's just pretend for a moment that it's there's supply voltage, I don't know what, 6 volts, 12 volts, something, whatever. Um, we're going to look at the program. Actually, I should illustrate. So the motor itself is just DC, positive and negative, and then we've got two sets of inputs. That's the 1A, 2B, 1A, 2A, 3A, 4A, and then we've got 1, 2 enable pin, whatnot. So we're only using one channel. We're not using two, and we're using two outputs, and the outputs are connected to whatever pins on the DC motor. It really doesn't matter. We have output one connected to positive, output two connected to negative, but it really doesn't matter in the grand scheme of things. Um, but let's take a look at our program. So we've got our speed control, which is connected to number 9, pulse width modulation for what we're doing here. And then we're setting our ends as, actually it says 7 or 8, but that's, all right. I made a little adjustment to it. I didn't have the right pins hooked up. But anyways, let's so yeah, our enable pin is 9, and then our two inputs are 7, 8, respectively. We set our pin modes to out. We declare stop motor, which is a function down here. We set both our ends to low. We set our enable to 0. Okay. Um, and then we're going to loop. We're going to set motor. Let's look down at our set motor function. We're going to take an integer, that's our speed, pulse width modulation, and then Boolean forward. So we're going forward, or we going in reverse. Pretty simple thing here. So int1 would be I would be going in reverse, int2 would be, sorry, int1 would be forward, int2 would be reverse. It's pretty simple. Whether or not this is actually how it's, the specifics don't matter for this demonstration. But it's not like we have it hooked up to a wheel or anything. But otherwise, and we are constraining the pulse width to 255 here. Um, but yeah, so we're going through the loop. We're going to go forward at 50%, then we're going to go forward at full speed. We're going to stop it, reverse 50, reverse full, stop it. So 3 seconds, 3 seconds, 1 second, 3 seconds, 3 seconds, 1 second, just repeating in a loop. So stopping. Oh, 50% full, 100% full, stopping, 50% reverse, 100% reverse, stopping. So yeah, pretty simple. So the only thing in theory that the Uno is handling is the logic signals. Again, just pretend that there's a supply, external power supply somewhere over here. Then we're going to talk about gear motors. Well, this is really just a DC motor with a gearbox, which is just a set of reduction gears. And this trades speed for torque. Now the DC motor can move wheels, arms, or any other kind of mechanisms, and it's built around a gear ratio, which I'm saying is X colon Y, and it's basically the number of motor revolutions against the number of output revolutions. The same driver modules that can be used for DC motors can just be used for gear motors because the motors are the same really between the two. You're just trading speed for torque. And then we've got servo motors. These are actually a combination of a couple of things. Small DC motor, you got a gearbox, you got a position sensor. Usually this is a potentiometer and some kind of control circuit. The desired and the actual position are constantly checked and compared, and then it adjusts accordingly. It's got three wires, power, ground, and a signal wire. You'll probably find an S90 in your hobby kit. They're just incredibly common. You can get like 10 of them for almost nothing. They'll operate on 4.8 to 6 volts, so 5 volts, no problem. You can operate these without a driver, um, right directly off the Arduino or whatever you get them with. They have approximately 180 degrees of operation, about 1 to 2 kilograms per centimeter in terms of torque. So not a whole lot, but you can move some very lightweight things as needed. Um, and this is just a very basic model that you might find in hobby kits right here. Oh, actually, no, this version is not what I'm thinking of. This has continuous rotation. You can get them either with a limited rotation or continuous. All right, let's take a look at the same thing in Simu IDE. Um, Same program here. So let's run it. Doing our forward sweep, back, going to center, wave, shake. So it looks physically a little bit different, but it's a different simulator. The same idea though. Here's a simple example of using a servo. This would probably be a micro servo, but uh, we don't really have a choice in walkway or single, double, or cross. Really, all we have. So let's look at the program. Well, we use a servo library up here at the top. We set our servo object. We have our setup. We attaching to pin number 9. We're setting a random seed, I guess, from, let's see, why are we doing that? I'm actually not entirely sure. Yeah, I didn't write the program. Um, but yeah, the first thing we're doing is we're sweeping from 0 to 180. Okay, using a for loop here. We're delaying each step 15 milliseconds, sweeping back, waiting a second, moving it to a direct, right in the middle, so we can write to a direct position. And then we're going to do a wave motion. So we're moving to 60, waiting 120, waiting, doing that a couple of times, going back to center, doing some random positioning here. Oh, that's why I guess, yeah, that's why we wanted the seed question mark. Um, and then doing a fast shake here at the bottom and rinsing and repeat. Let's see what that actually looks like. There's a first sweep, there's a second sweep, center, a wave. All right, there's our program. All right, here's another little servo test. In this case, This is, we're going to be controlling our servo here at the top with a potentiometer on the bottom. Um, the serial monitor is just going to keep flashing what the potentiometer and the servo angle are at. But this is a pretty simple program. We're just defining our pins up here. Obviously, one's connected to analog, one's connected to pulse width modulation. We're attaching, and then we're mapping values here. So as you see, it'll turn at. Now, one's mapping from 1 to 1023, the other's mapping between 0 and 180. So it's not one for one. See, we can turn that. And again, this is just, in a way, this is just a model in practice, but this can be turned into so many other things too. Then we have stepper motors. They have a very fixed set of positional steps. Each step is a precise number of degrees, allowing for a very precise control over position, distance, and speed. There's no need for any kind of complex feedback system because we have precise control over each step. A common setup is like 1.8 degrees per step, 200 steps per revolution. Okay. 1 pulse per step and 200 pulses for one full revolution. We also have a concept of microstepping. That's where you can break down a single step into even smaller steps. There's also unipolar versus bipolar stepper motors. These are fundamentally different, although the operation may appear the same. This has to do with the coils and the actual motor. Unipolar energizes different halves of the coil without reversing the actual current flow. Bipolar, it uses a complete winding on each coil. The driver must reverse current through the coils to change magnetic polarity. I've listed out some pretty common motor types and some pretty common drivers. This obviously needs a driver as well. Usually you can find these stepper motors. At least the significant ones can be a little bit more expensive, um, but it kind of depends. There's kits that they'll come with. They'll come sometimes come with the driver boards, so you don't have to really heavily go looking. All right, here we have a stepper motor with a driver board here on walkway. So let's see what it does. We set a stepper pin and a direction pin on the Arduino. So the Arduino is only using 2 pins, well, power and ground for the logic signal. I've also got the motor set to a VCC, but you can ignore that entirely. We don't have to worry about the enable pin. We're not using the micro step pins. We're just short circuiting reset to sleep because reset is already high. Um, if I was doing this in real life, I'm sure there'd be a better way to do this. But we're just setting step and direction. And then the other everything else for the most part is 4 different pins that are going to the step motor here. 2B is going to A minus, 2A is going to A plus, 1A is going to B plus, 1B is going to B minus. Okay. So what is the actual program doing? Well, we're doing the setup for the 2 pins and we're writing a directional pin I for the initial direction. Okay, pretty easy. Um, for the loop, we're starting with a slow continuous rotation forward. All right, so we're going to be doing delays of 1200 microseconds low. We're doing high, 1200 microseconds low, high, all the way up through the number of revolutions, which we've established as 200 up here. And then we're going to be doing the opposite. We're going to be going into reverse quickly. So it's only going to be 600 microseconds instead of 1200. And then we're going to do some burst stepping, jerky, kind of back and forth here. And then we're going to do some micro stepping, I guess, but we're not using the actually micro stepping pins. Now, I think one of the limitations is we can only do half steps with that. I might make another program that shows the micro steps, but again, this is just an intro video anyways. So let's see how this looks. So we have control over speed, direction, and position. Now we have access to microcontroller dev boards. What does this mean for working with motors? Well, a microcontroller can perform an intelligent drive to a sensor and coordinate processing and response. Change in a motor's response can be a response to an input, such as that of a sensor. This could be a sensor directly related to the motor. Perhaps it responds to thermal conditions and acts accordingly to avoid degradation or damage. It could be a sensor detecting an obstacle. The motors could be turning wheels on a small RC car that could then avoid the obstacle. It could detect that the motors are now in reverse and blink backup indicator lights on a small RC car. This doesn't negate the need for driver boards or external supplies, as a microcontroller dev board has limits to the voltage and current it can safely provide to motors. Now, just to wrap things up here, a motor is a machine that converts energy into electrical motion. In the case of this video, we were talking about electric motors and specifically ones that pertain to hobby electronics on a small scale. We mentioned rotary motors versus linear motors. Many motor characteristics include things such as torque, speed, and power. We discussed DC motors, gear motors, servo motors, stepper motors, and brushless DC motors. We also mentioned how most of these need driver boards. We discussed some of the options they have and why they're necessary. We also talked about how microcontrollers can be used with motors to provide intelligent processing to the use of motors. Well, until next time, have a good one.